All right, hello there. We're going to be working on graphing rational functions. And what makes a rational function special is that it has some asymptotes. This is a parent function, y equals 1 over x. This is one of our parent functions that we've learned this year. So make sure we understand the word asymptote. Whoa, my pen is not working. Let's try that again. There we go. Okay, so the word asymptote, and basically it's an invisible line or an auxiliary line that our graph is going to approach, but it's not going to cross. You can never cross a vertical asymptote, but you can cross horizontals, and we'll get into that in another video. But right now we're going to be doing basic graphs with transformations, up, down, left, right, flipping, and stretching and shrinking. So let's go ahead and just review what our parent function is for a rational function. First of all, you guys know that x cannot be 0 here. We've been working on simplifying rational expressions, and we know that this is a problem when x is 0 in this function. So we are going to have what's called a vertical asymptote at the line x equals 0. It'll be this dotted line. Always dot it. Please do not dash it. Please do not make it solid. You can dot it or dash it. Now, having said that, x can't be 0, it doesn't matter what x is. Positive, negative, a fraction, an improper fraction, doesn't matter what x is. Y will never be 0. There's no value of x that you can put in there that y can be 0. That y will never be 0. So we have what's called a horizontal asymptote at y equals 0. And again, this is our parent graph. So this obviously is going to change. I do like you guys to label your asymptotes on the sides, please. And your graph is never going to cross either one of these asymptotes for the parent graph. Before we talk about domain and range, let's actually graph it. So a lot of times what I do is, I don't know if you guys have a lot of room on your papers here, but I'm gonna show you a couple, plug in a couple numbers for x. So 1, -1, 2, -2, how about a half? Oops, and a -1/2. Sorry, I'm kind of scribbling here, -1/2. Okay, so if I plug in 1 for x, I get 1 over 1, which is 1. If I plug in a -1 for x, I get a -1. If I plug in 2, I get a half. If I plug in a -2 for x, I get a -1/2. If I plug in a half, 1 divided by half is 2. 1 divided by a -half is a -2. So if I were to come over here, and let me change colors here. If I were going to change colors here, let's see, I would have 1, 1. I would have -1, -1. I would have 2, 1/2. I would have -2, -1/2. If I have 2, I already did that one. I guess that's all I had. And of course, it's not defined when x is 0. When x is a -1/2, or excuse me, 1/2, I get 2. When x is a -1/2, I get a -2. Now, if I keep giving bigger values of x, let's say 10, that's 1/10. If I go a million, that's 1 over a million. Do you see that that will never be 0? So I'm not going to graph these very well with my pen here, but it's going to get closer and closer to 0, but it's never going to cross it. Never going to cross that. So I know I nestled up to it and it kind of went up here, but it's just because I can't draw with this pen. So, and also it nestles up to the vertical asymptote too. This is never going to cross that vertical asymptote. Over here, I can, if I plug in like -1/10, that's going to give me a -10. So it's never going to cross this asymptote, and it's never going to cross this one. So make sure you have arrows. And again, I'm going to do the best I can with the graphs. Graphing is not my forte when it comes to using, when I make videos. So just got to hang in there with me. But it doesn't cross, and it just kind of, it gets closer and closer to the asymptote, but it doesn't cross it. So I'm not trying to dot those, but I'm just trying to show you. The key points here are 1, 1, and a -1, -1. Remember, all of our parent functions have some points that we need to remember to help us graph quick graphs, right? So this one has the critical points, 1, 1, and a negative 1, negative 1. And you have the asymptotes. Now, of course, we're going to slide this graph to the left, slide it to the right, up, down, flip it, stretch it, all that stuff. And so our key points obviously are going to change, and I'll review with you how we do transformations in just a second. So our domain, all real numbers except for 0. You are always going to use interval notation, please. Parentheses, of course, throughout. Your range, how low does it go? How high does it go? Negative infinity to 0, union 0 to infinity. So there is your parent graph for a rational function. All right, so let's also review a little bit about transformations. I'm trying to get this up. I'm not doing very well. All right, so here we're going to review some transformations. We'll use HK again. Remember, K is up or down. You do what it says. If it's plus K, you go up. If it's minus K, you go down. Remember, on the left and right, H is your left and right. And remember, you do the opposite. So this is your left and right. It's left if it's positive. It's right if it's negative. All right. So remember, you always do the opposite. A is going to be your vertical stretch or compression. We will not be talking about any horizontal stretches or compressions because honestly, it's the same thing as a vertical. So just we're not going to be talking about stretching the X or the Y. I mean, stretching or compressing the X, just the Y value. So A is your vertical stretch or compression, okay? So I want you to write an equation that goes left 3 and up 2. So we'll write it here, y equals, we can use f of x or y, it doesn't matter, okay? I have no vertical stretch or compression, so my a value is 1, no stretch or compression. Left 3, so that's with the x, that's what it's affecting the x value. It's taking it to the left, so we write plus 3, and up 2 means plus 2. So up 2, left 3. Now, we're not going to answer these yet until we get our parent points, or our new points, not parent points, but our new points, okay? All right, so our parent points are 1, 1, and a negative 1, negative 1. Now we're going to ask ourselves what's affecting the x value here and what's affecting the y value. So my x value is going left 3, so I'm going to be subtracting 3. And actually, why don't I put this up here? So I'm going to be subtracting 3 from my x's, and I'm going to be adding 2 to my y values. So this is your, if you guys remember, we did this with all those transformations many months ago. So here we are going to be doing minus 3 because you're going left, plus 2 because you're going up. So this new point is going to be a negative 2, 3. Subtract 3 from the x, add 2 to the y value. Same thing with this parent point, 1, 1, negative 1, negative 1. These are the two parent points. Negative 1 minus 3, negative 1 plus 2, and those are your two parent points. So we're going to have negative 2, 3, and we're going to have negative 5, 1. And we could have done our asymptotes first, but I just thought I'd get these on here first. Okay, so horizontal asymptote. If your graph was at your horizontal asymptote, was at y equals 0, but you made it go up 2, you have a horizontal asymptote at y equals 2. Your vertical asymptote is normally at x equals 0, but you're moving it to the left 3 units. So that's x equals negative 3. Make sure that you're using x for vertical, y for horizontal. 1, 2, 3. I think I miscounted on that one, didn't I? Let me go back and fix that point. That's supposed to be negative 5, 1. Oh, I did. And this one's supposed to be negative 2. All right, something's not right. Hold on. I figured it out. I cannot subtract 3 from 1. That's a negative 4. Sorry, sometimes when you're just talking and gabbing away, Let me do this in blue. -4, 1, sorry. Okay, and then when you graph it, oops, I totally missed it. Make sure you hit your critical point, and you're going to snuggle up to those asymptotes. Try not to touch them. Don't cross them. Don't forget to put arrows on the end. So I kind of messed up that point, sorry. All right, so, but that doesn't change those. All right, and then once you get it graphed, you can do your domain, -infinity to -3, union -3 to infinity, your range, -infinity to 2, union 2 to infinity. Now this next one, I'm going to go ahead and do, I'm going to work on the asymptotes. A stretch or compression doesn't affect asymptotes. I want you to remember that. So your normal asymptotes intersect at the origin, right? So this does not move left or right. It goes down 5. Well, we're going to go ahead and write this as a vertical stretched by 3. So the 3 is on top. There is no left or right, so x is all by itself, and then it goes down 5. So you still have a vertical asymptote at x equals 0. I don't think I labeled that on the other graph. And then down 5. 1, 2, 3, 4, 5. This is, my graph doesn't print very well when I do these PDFs. So this is y equals a -5. Okay, so let's talk about what's happening here. All right, nothing is affecting the x values. This 3 is a vertical stretch. It's affecting the y value. So x stays the same, and then you're going to multiply your y by 3 down 5. So you're going to take your 1, 1, and your -1, -1. Your x value stays the same, but now you're going to multiply the y value by 3, subtract 5. So 3 minus 5, -1 times the -3, excuse me, times 3 is a -3, minus 5 is a -8. Okay, we're going to come over here and graph these guys. 1, -2, and then -1, -8. That's 5, 6, 7, 8, right on the edge here. And then do your best to graph these. They should not be L-shaped. They should really be curvy. The bigger the stretch, the bigger the curve. And it should have some kind of symmetry. See how there's a little bit of symmetry here between the intersection of the asymptotes? It's about the same, not about, it's exactly, you know, over 1, up 3, down, left 1, down 3. See how it's very, very symmetric. So try to make them curvy so that they are. All right, your horizontal asymptote was -5. Your vertical asymptote was x equals 0. Okay, all right, let's try the next one. This one has a reflection, and let me see if I can make this a little bit better here. Let's do that. All right, so let me change colors as well. It's getting a little messy up there. Okay, so reflection over the x-axis, that is called a vertical reflection when it reflects over the x-axis. Let's write this equation. So we'll put a negative up there, right 4. So let's make sure we do the opposite on the bottom, and up 2. Now, it does not have a stretch or compression, so there's just going to be a 1 up top. All right, so we're going to do x plus 4, because it goes, oh, excuse me, that's a lie. Sorry, I misread it. It goes, if you're moving your value of x to the right, and then up 2, and you're multiplying by -1, so -y plus 2. The negative is affecting the y values. We'll find the new points first. Okay, so add 4, so that's 5. -1 plus 2 is 1. -1 plus 4 is 3. -1 times the -1 is 1. 1 plus 2 is 3. So our new points, not parent points, our new points are 5, 1, and 3, 3. All right, so if it went up 2, you have a horizontal asymptote at y equals 2. It went right 4, so you have a vertical asymptote at x equals 4. Okay, and then a vertical reflection, if you think about what's going to happen to the parent graph, you're going to basically be flipping over this x-axis. Our points will show that. Here's 4, here's 5, 1, and 3, 3. So these will be in opposite corners. I just got through telling you make sure they're not L-shaped, but that one I couldn't avoid, so there you go. So there you go. Sorry, that's terrible. Just make sure I can see these parent point or our new transformed points. Domain, -infinity to 4, union 4 to infinity. Range, -infinity to 2, union 2 to infinity. Okay, let's try the next page. Okay, so graphing other types of rational functions, like rational functions that are in different forms, I'm going to take a much different approach to this. And this is really going to apply what you've been working on in this unit as far as how to simplify rational functions, factoring and finding the domain restrictions and so forth. This is the whole reason why we learned how to do that. Okay. So a rational function is where we have a polynomial over another polynomial. And of course, the denominator can never be 0. And so that's really important when we graph. We're going to be gathering information. I'm going to do this in a couple videos, but we're going to be gathering information to eventually graph these. So right now we're not going to be graphing anything yet. We're just going to be working on finding critical points to make a graph, and we're not using Desmos or a calculator. Graphing calculator to help us. So let's first start with all the things x value. Okay, we're going to start with some x values. We'll get into some y-intercepts. We're going to be focusing on the domain and those restrictions. Okay, so again, polynomial over a polynomial. You guys are going to be doing a lot of factoring here. So the domain of a rational function consists of all the values for x for which the denominator cannot be 0. So let's figure out basically what our restrictions are of this problem, and we're going to factor. Okay, so this is x minus 3, x minus 4 over here, x plus 4, x plus 5. So from what we learned already in this unit, we already know that x cannot be -4 or -5. If we think about this on a number line, it can be all real numbers except for these two numbers. So if we're going to look at it from a little bit of a graphic, I guess, you would have open circles on -5 and -4, and your domain is everything else. So of course we're going to always write this in interval notation. X cannot be those two numbers. So -infinity to -5, union -5 to a -4, union -4 to infinity. It's possible to have several unions in your domain. It just depends on how many restrictions your domain has. Okay. Now, so that's the first thing we're going to look at. Now, we want to know what's happening at these two x values. I want to know there's going to be special things that happen to your graphs. It might be a hole, like literally an open circle, or it could be a vertical asymptote. And that's what we're going to be deciding what are they. Okay, and just so you know, these two are asymptotes, and I'll explain that in a second with a different example. So holes are found by canceling factors. Coefficients aren't factors, just so you know. We're talking about factors. It has to have a variable. So if you can factor and then cancel something from the top and the bottom, that means you have found the x-coordinate of the hole. All right, and then you're actually going to be finding the y value of the hole by plugging in that value of x you just found back into the simplified equation. Okay, so we're trying to figure, and then when we graph it, you literally do an open circle on your graph. In the above example that we just did, you didn't cancel anything out. Nothing, let's pull that back up. There were no common factors. There's an x minus 4, but not a plus 4 or a minus 4 on both. Okay, so there's nothing canceled. So you do not have any holes. You didn't cancel anything. You just have two vertical asymptotes for that example. These breaks in discontinuity, whether it's a hole or a vertical asymptote, it's very important that we know which is which. You can have multiple vertical asymptotes, you can have multiple holes, you can have some of each, but it's really important to understand the difference. All right, a hole again is when you have a canceled factor. All right, on the top and the bottom. All right, vertical asymptotes we just talked about, you can't cross them. And then when we go to graph them, you must have a piece of the graph on the left side and the right side of every vertical asymptote. So we're not graphing in this video, but that's just a little tidbit of information there. All right, the other points we're going to find are x-intercepts. Those are solutions to the simplified numerator, or I like to say the zeros of the simplified numerator. Y-intercepts plug in 0 for x, and I always like to use the original. You have to use the simplified for x-intercepts. Absolutely have to use the simplified. Otherwise, you're going to get your asymptotes. Your y-intercept, I would use the original, but you can use the original function or you can use the simplified. It doesn't matter. I always like to use the original because what if you factored wrong? And that would be bad. So I just use the original. Plus, it's really easy to cover up the x values. If that's 0 and this is 0, I can just cover up the x's and I can see that my y-intercept is a -1. Okay, and I'll get into that in a second. Let's go ahead and just do this problem. All right, so the first thing to build ourselves up to graphing, we got to find our pieces of information. So the first thing you do is you look at this denominator and tell me what x cannot be. You can factor if you want to. Yeah, might as well factor x minus 1, x plus 1. But don't cancel anything yet. You need to state the domain before you cancel. That domain x cannot be -1. So that is -infinity to -1 union -1 to infinity. The numerator has nothing to do with the domain. Absolutely nothing. Okay, I might do the y-intercept right now. The y-intercept, plug in 0 for x, and you get 0, -1. Please make sure you're writing that as an ordered pair. Okay, so I'm going to change colors here. All right, so we have a canceled factor. X plus 1 cancels, and we're left with x minus 1. So I want to know, this is all about what is happening when x is a -1. That's the whole point of this part of the notes. What is happening at a -1? Well, if I cancel this, the x coordinate of that hole is going to be a -1. Plug it back in to the simplified equation, and you get a -2. So in other words, you're plugging it into your simplified equation, which is x minus 1. So we get -2. So on your graph, when we eventually graph that, you're going to put an open circle at that point because there's a hole there. There's a point of discontinuity there. Vertical asymptotes, none. Once you have canceled, if you don't have a denominator anymore, you don't have any other restrictions. So there's no vertical asymptotes. Your x-intercepts are zeros in the numerator after you have canceled. So if I have x minus 1, think about that as x minus 1 over 1, right? What's the 0 of that numerator? 1. In other words, you are plugging in 0 for y. So I don't know if that helps, but I just assume just look at the numerator and decide what value of x is going to make that 0. So that's your x-intercept. Okay, make sure you write that as an ordered pair, please. All right, let's try another. All right, we're going to factor it. State your domain. X cannot be 4 or -2. So it's everything but those two numbers. So -infinity to -2. Make sure you go in order from low to high. negative 2 to 4, don't forget that part, union 4 to infinity. So it's all real numbers except for negative 2 and 4. If you need to draw that number line to help you, by all means, do it. Okay, it's all real numbers except for those two numbers. All right, so now we're going to go ahead and cancel. And let's, if we cancel, that means we have a hole. The x coordinate of that hole is a negative 2. Simplify that. And to find the y coordinate of the hole, we're going to plug in negative 2 in for each of these x's. So negative 2 plus 4 over negative 2 minus 4. So you get, you get 2 over a negative 6, which is a negative 1/3. So again, I'm trying to figure out what is happening. What are these places of discontinuity here? I'm going to have a hole in a negative 2. And then to find the y value of that hole, you're going to take negative 2 and plug it into your simplified equation. Okay, vertical asymptote is what's left. So you're going to have a vertical asymptote at x equals 4. X-intercept, 0 of your numerator. Y-intercept, plug in 0 for x. I like the original, but you can use either one. All these x terms will go to 0, so you have 8 over negative 8, so you have 0, negative 1. Okay, we're going to do a whole bunch more, so feel free to speed up, repeat, whatever. But there's all kinds of different types of factoring in here, so I want to make sure that we are straight before getting into the next part of the notes. Okay, let's do this. X minus 3 over x minus 3, x minus 5. I'm not canceling until I answer that domain question. I always write what x can't be here, always. I don't care if you do, but it's really good because then I'm going to decide, hey, where does 3 and 5 fit in down here? Okay, so be careful every time that you guys are canceling something. Maybe you should be replacing it with a 1. This is a great example why. These x minus 3's cancel. You need to put a 1 up there. The x minus 5 is in the bottom. There's a 1 on top. So be careful with that. That's a mistake students make all the time. Now I just canceled a factor, so that means I have a hole. The x coordinate of that hole is 3. I'm going to take that 3 and I'm going to plug it in for x into my simplified equation, and 3 minus 5 is a negative 2, so I have a hole at 3 comma negative 1/2. That means I have a vertical asymptote at x equals 5. So these are the two places of discontinuity in our graph, and there's a hole here at 3 and a vertical asymptote at x equals 5. X-intercepts. Notice that's 1 over x minus 5. There's no variable in the top, so this one doesn't have one. Y-intercept, doesn't matter, simplified or the other. Negative 3 over 15 is going to be a negative 1/5. Okay. Okay, I need to get, one of these signs have to be negative. We got to choose wisely here. We got to make sure we get a positive 1x. So this will be a plus here because that's going to give me 2x and a negative 1x. So that's supposed to be an x right here. Okay, all right, so x cannot be negative 1 or positive 1/2. I can cancel the x plus 1's. If I cancel a factor, that means I have a hole. The x coordinate of the hole is a negative 1. And again, these have to match these. Whatever you have here has to match these restrictions. Plug in a negative 1 into the simplified equation. I'm going to need some scrap work here. So negative 1 minus 1 over 2 times the negative 1 minus 1. So we get a positive 2/3, and that means that x equals 1/2 is your vertical asymptote. X-intercepts, 0 of the numerator, which is 1. Y-intercept, plug in 0 for x. You get a negative 1 over a negative 1, which is a positive 1. And again, I could have put 0 in here. I still get negative 1 over a negative 1. All right, some more factoring. Let's take out a negative 3 here, and we get x minus 4. All right, and then we're going to cancel. Okay, that means we have a hole at 4 something. And take that 4, plug it in here, so that's going to be a negative 3 over 5. Vertical asymptote is at x equals negative 1. Don't forget it's an equation. Don't just write negative 1. It's a vertical line. It's an equation of a line. Okay, there's no variables in our numerator, so this does not have an x-intercept. Our y-intercept is 12 over a negative 4, which is a negative 3. Okay, let's keep going. One more example, and then we'll be done. All right, let's take a negative 2 out of that first. Sorry, my little thing is in the way. Oh, I don't know if that's any better. I didn't finish factoring, I know. I'm getting my domain all set up here. Everything but 1 and 4. All right, so that's going to be a negative 2, x minus 4, x plus 2, over x minus 4, x minus 1. All right, now that's really in my way. All right. All right, what do we can cancel? Right here, x minus 4s. Okay, so that means we have a hole at 4 something. Let's take that 4 and plug it in. So we got negative 12 over 3, which is a negative 4. That means we have a vertical asymptote at x equals 1. X-intercept, 0 of the numerator. This constant doesn't affect it. What makes that 0? Negative 2. And then the y-intercept, plug in 0 for the x value, and you get all the x values, you get 4. Okay? All right, so hopefully, guys, this was helpful, and we'll find more information, but this is all the stuff that affects x, except for the y-intercept, of course, but this is all domain stuff. All right, see you next time.